Hello, my name is James Black, and I'm going to be talking about a comedy of errors designing a reactive application. So a client asked me to build a mobile application to have a secure messaging client. I decided the easiest way to do it is to just have a Windows server with the web server and database on it. I told him that we'd be down about 3 hours a month, which is 99.5% uptime. My goal was a 98% uptime, which is down 14 hours a month. The client was unhappy with that, so I switched it to Linux instead of Windows. We're down 1 hour every 2 months for updates, and it's a 99.9% uptime. The client was much happier. So then we get ready to start testing, and during the pilot testing, the hard drive fails. We're down for a whole day. So much for my 99.9% uptime. The client was very unhappy. But I didn't take into account the fact that we may have power outages, hardware problems, the ISP may have a failure, there could be any number of issues. So, after looking at different options, we decided to move to the cloud, AWS. And so we're using AMI for the web server and an AMI for the database. We're only down 4 minutes a day, which is 99.99% uptime, and someone else besides me is taking care of security patches and just patches in general. So, much nicer. We go to doing some pilot testing. During the pilot testing, we end up finding that there's too many client connections. So, then I realized, oh, we only have one web server. So I just turn on autoscaling. And that solves that problem. So now we're going to go into more extensive beta testing up with 10,000 people. And then users still complain about connection problems. So I look into it and I realize, oh, we're only using one database. That could be the problem. So, because each of these web servers all connect to just one database. So then I run into Brewer's theorem. You get to pick two of these issues where you can have either partition tolerance, which means that you could be on different partitions. You can have consistency, so all of your nodes can have the same data all the time. Or availability, which is just how often are you available. Since we're looking at a distributed database, we have partition tolerance, so we either pick consistency or availability. Told the client that I'd rather go with being always available, which means that some people will have messages and they may not get them right away. There might be a bit of a delay as different nodes are getting the data. But we went with a distributed database. So all of the nodes can speak, all of the web server nodes can speak to all the database nodes. So problem solved. So this is what the final infrastructure design looked like. And we were quite happy with that. So they continued on with their testing, and we had an application crash. So now I started looking at the fact that it appears that there's a problem with the fact that we are connecting to too many to the web server. There could be too many connections going to a web server at times, depending on how it fits into the round-robin scheme. So I might need to try and change it. We could use an ESB, but this introduces latencies because every one of these connections can slow down the system. I could use multiple web servers in a chain. So a microservice approach where I could break up, so I could have a user web service, a team web service, a password web service, and they could all be connected to these distributed database. But then I could still run the same problem depending on what's going on. So I decided that we could just move to Docker, because the problem was that when you have too many connections going at one time, So we normally have 1,000 people using our system. If over a 5-minute window it jumps up to 1,000,000, auto-scaling can't scale that fast. And then we're still back to we're hitting too many connections going to the few web services that are up, and the system, some of the clients start to crash. So then, as we continue to look at the logs, we start seeing that we're seeing a higher utilization than we expected, and the problem might be the client-server paradigm could be an issue. And that's because and this is one example where we're trying to validate, we want to get a token. So the problem is that as you start to go through each call, you block and you wait until you get the response back. So that's a lot of waiting, and that ties up a lot of threads. So I think there might be some issues with the client-server approach. So thinking back to my Erlang days, there was a concept in the 70s about actor systems. And so the idea is fine-grained, massively parallel distributed computer systems with no shared state, and they have maximum concurrency. And in Erlang, this is an example of some actors sending messages to each other. So I started looking at actors in Java. And so the way that it works out with Akka is you have one, like in my case, the web server layer will have a login service. The get token method in there will start with an actor, the controller actor. The controller actor then will pass messages to a get token actor. None of these actors share state with each other. They only know about each other from the messages that are passed to each actor. But the advantage is that if one of these actors crashes, one of the supervisor actors above them will detect that and can then handle it. They can restart the actor, they can just pass back an error message. There's various options they have on how to handle when there's a crash. But then these actors just keep passing messages down to each other. The nice thing about this is actually not client-server, because it's more of a send and forget. So for example, when the user DAO, select user by username, gets the information from the database, it will actually pass back a message to the login controller. So these other two in between don't see the response. They don't care about the response. And then it continues on to validate the answers, and then it generates a token. And then this is how the message is sent back to the controller actor, and this is how the entire system would look, with calling lots of actors. So this is how the deployment process came down to that we looked at. The developer commits code, the code is built and tested, a Docker container is created, we deploy a container, we use auto-scaling, and we go to a Aurora database. And all the configuration information is actually in a S2 directory. So we started with a simple mobile server, we moved to the cloud using AMI. Then we had to go to a distributed database, then we went to Docker instead of AMI. And then we looked at the fact that we needed to go to Akka to help not be tying up different threads. And this is a very simple application with more complex applications, with more applications that make up a system. These can be done in a reactive way also, but the problem is there's other challenges that you have to encounter that I've just glossed over here. And then there's other languages that could be better, that could be used, that would not have some of the weaknesses that Akka has. One of the problems with Akka is that right now, if I know the nodes for my servers, and if I know the IP addresses of my nodes, I can create a cluster. If I create a cluster, then my actors can be spread anywhere on that cluster. They don't have to be on the same machine as what they were called by. They could be on some other machine. So you can use local and remote actors. But when you are using autoscaling and your VMs are coming up and down, you don't know which VMs are around, the actor discovery is an issue. There's other approaches to other languages that can be used to solve that problem. The other issue is the fact that when I called into the web service originally, I'm using Jersey. And then Jersey has to turn around and then use an actor paradigm. It would be nice if I could use actors from the very beginning, but that would be a longer discussion. And that's it. Thank you very much.